Welcome to this lecture of calculus. In this lecture, we shall study about how to evaluate the periodic equation of a curve. But before defining what we mean by a periodic equation, we shall recall one previous concept as how do we define the angle between the radius vector and the tangent to a curve. So this is a review. We have defined it like this. If phi is the angle between the radius vector and the tangent to a curve, which is given in this way, r is equal to f of theta, in fact in polar coordinates, then we have this tan of phi is equal to r d theta by dr. Now let us draw one figure here so that we can first understand what we mean by the period equation, actually what we have to do in the period equation, and then we will define the actual definition of the period equation. So here let's consider this graph. So we shall consider this graph. Now here we have, this is our curve, r is equal to f of theta, and suppose we represent this point P with the coordinates as r theta, then this blue line, which we shall represent by t, and we shall mention t here, this is the tangent to the curve at point P. Now here we shall represent this point by O, which is the origin, and now this point O connecting with P by this green line. This is the distance r, or the length of this OP is equal to r, and we call this OP as the radius vector. Now we draw a perpendicular from this point O onto this tangent T, and suppose it meets the tangent T at the point L. Then this OL is the perpendicular from the point O, and O is called the pole here. Then we assume the length of this perpendicular is equal to P. Now here, using this figure, we can define what we mean by the period equation. The period equation is actually defined as a relationship between the length of the radius vector r and the length of the perpendicular from the pole to the tangent at that point. So we mentioned the definition of the period equation here. The period equation of a curve is a relationship between the length of the radius vector r and the length of the perpendicular from the pole. So this is the definition of the period equation. Now here, as we have already mentioned, this O is called the pole, and perpendicular from this O onto the tangent, which meets the tangent at the point L. This OL length is supposed equal to P. Then the relationship between this I and P, which can be obtained by using the given equation, is called the period equation of the curve. Now here we shall try to understand how do we obtain this relationship between this P and R. Now if we look into this triangle OLP, which is the right angle of the triangle, and this is the angle phi, which is the angle between the radius vector r and the tangent d, then we already know that the tan phi is equal to r d r by d theta. So we have already this tan phi is equal to r actually d theta by dr. Now using this relationship between the angle between the radius vector and the tangent, which is given by this relation, we can compute the relationship between this P and R, which gives us the required period equation. Now in this triangle, OLP, which is right angle at L, we have this OL divided by OP. Now as phi is the angle between this OP and PL, so OP is the hypotenuse of this triangle and OL is the perpendicular. Therefore, we have here the relationship OL divided by OP, which is perpendicular divided by hypotenuse. We know it is equal to sine of the angle. So therefore, this is equal to sine phi. So this gives, but OL, that's equal to P divided by OP, that's equal to R. So this is equal to sine phi. So this implies P is equal to R sine phi. So we have got one relationship between P and R, but now it is in terms of the sine phi, we have to eliminate this phi from here. So, but before that thing, this implies this 1 divided by P. This is equal to 1 divided by R sine phi. So we are taking the reciprocal of the previous equation on both sides. Now this further implies 1 divided by P square is equal to 1 divided by R square, 1 divided by sine square phi. This is because we have taken square on both sides to obtain this equation. Now this further implies 1 divided by P square is equal to 1 divided by r square, and now we know that 1 by sine square phi is equal to cosec square phi. So this is equal to cosec square phi. So now this further implies 1 divided by p square is equal to 1 divided by r square. Now cosec square phi can be written in terms of cos square phi. So this is equal to 1 plus cos square phi. Now here comes the role of that relationship between the angle between the radius vector and the tangent and the given curve, which is r equal to f of theta. So but we have, so this can be written as, so this implies 1 divided by p square is equal to 1 divided by r square into 1 plus 1 divided by tan square phi. And this can further be simplified as 1 divided by r square into 1 plus, now we know that tan square phi, what's tan square phi equal to, so we have tan phi is equal to r d theta by dr. So this is equal to 1 divided by r d theta by dr whole square. So therefore we can express this as 1 divided by r square into 1 plus 1 divided by r square into dr by d theta whole square. So this further finally implies 1 divided by p square is equal to 1 divided by r square plus 1 divided by r power 4 d r by d theta whole square. So we have got this relationship between p and r in this equation now. This equation is actually known as the Peter equation. So this is our Peter equation. Now in order to actually finally obtain the Peter equation, we have to eliminate theta from this equation. Now let's take an example. So here we have an example where we need to evaluate the Peter equation of the curve r equals a into 1 minus cos theta, which we know this is actually the equation, polar equation of the cardioid. So we take up the solution. We know that the Peter equation of r is equal to f of theta is given by 1 divided by p square is equal to 1 divided by r square plus 1 divided by r power 4 into dr by d theta whole square. So this is the period equation. Let's call this as equation number 1. Now in this equation we need to substitute the value of dr by d theta that we can evaluate from the given curve. Now here r is equal to a into 1 minus cos theta. Then this dr by d theta. This is the derivative of r with respect to theta, and we know the derivative of cos is equal to sine theta, or equal to minus sine theta. So therefore we obtain dr by d theta is equal to a sine theta. So this is equal to a sine theta. Now using this in equation 1, so using this value in equation 1, we obtain 1 divided by p square is equal to 1 divided by r square plus 1 divided by r power 4. Now here we have dr by d theta whole square, so we can write this as a square sine square theta. So we can simplify this to, this is equal to 1 divided by r square plus 1 divided by r power 4, or we can write a square divided by r power 4 into sine square. Now here we got actually the Peter equation, but we have to eliminate this theta from here. That we can eliminate using the given equation. So now let's call this as equation number 2. Now from the given curve we have, now we are given r is equal to a into 1 minus cos theta. So this implies this 1 minus cos theta is equal to r divided by a. This further implies cos theta is equal to 1 minus r divided by. So this further implies cos square theta is equal to 1 minus r divided by a whole square. Now if we look in equation number 2, we have the value of sine square theta here. But we know what is the value of cos square theta, and we already have the relationship between sine square theta and cos square theta. So hence our sine square theta that we need in equation number 2, this we know this is equal to 1 minus cos square theta. So this is equal to 1 minus r divided by a whole square. Now let's try to simplify this. This is equal to 1 minus. Now expanding the square, this is equal to 1 plus r square divided by a square minus twice r divided by a. Now when we further simplify this, this becomes twice r divided by a minus r square divided by a square. So this is the value for sin square theta. And using this value of sin square theta in equation 2, we obtain the left hand side is 1 divided by p square and the right hand side is 1 divided by r square plus a square divided by r power 4 multiplied by this sin square theta, which is equal to 2r divided by a minus r square divided by a square. So we have completely eliminated theta from here. Therefore, this is our equatorial equation. Now we just need to simplify it. So we can write the right hand side as this is equal to 1 divided by r square plus, now let's multiply this thing. We can cancel one of the r's here, a square divided by r power 4 into 2r by a. This becomes 2a divided by r power 3. Then minus, now a square and a square is cancelled here and we are left with 1 divided by r square. Now we can see 1 by r square, here we have minus and 1 by r square. So therefore this implies 1 divided by a square is equal to 2a divided by r cube. So this is the simplified form of our Peter equation. So therefore this is our recurrent Peter equation. This is the recurrent Peter equation. So this is how do we compute the Peter equation of the curve when it is given in polar coordinates. Now suppose if we are given a curve in a Cartesian coordinate, then we can simply convert that equation into the polar coordinates by the substitution x equals r cos theta and y equals r sin theta. Now here we write one exercise for practice. So this shall be the exercise for practice and this completes this lecture.